Good afternoon, all. Welcome to the Samvaad talk by Professor Nandita Rao. I'll quickly do the formality. Uh, Professor Nandita Rao joined the institute in November 2017, last year. So that's 2 months before me joining here. So probably it would have been more apt if Nandita did the introduction to me than me doing the introduction for her. So Nandita did her B in Electronics and Communication Engineering from PS Institute of Technology in Bangalore, and then she worked at Intel Technologies for 6 years, again in Bangalore, and then she moved to IIT Bombay for her PhD. So she completed her PhD last year and then joined the institute here. So now, so Nandita will be talking on challenges in processor design, performance and security. That's the subtitle, right? Yeah. I personally look forward to the talk due to the last word, security. Yeah. Thanks.
This talk is slightly different from the ones we have seen before, in the sense that so people have always spoken about the research they have done already. So mine is more of a talk based on the research topics that I'm planning to do. So this is quite different from the PhD work that I've done, and therefore this is the research area that I'm planning to work on, or I've just started to work on. So that is slightly different from the other talks we've had so far. Okay, so does anyone recognize this? Anyone recognizes this, what this is? Yeah, so this one, so this is, right, so this is called the ENIAC, and this is just the first left half of the computer. Okay, so this is the left half of the computer, which was in the 1940s, and so this was based on mechanical parts or gears, that is basically moving parts, unlike the transistor based design that we have today. Okay, so in the 1940s, so this was the computer we had, and it required tremendous air conditioning to maintain the system. It was highly unreliable because if you had to program, you had to physically move the gears and put it in a particular position for it to work. And it was based on vacuum tubes. And for the first time, they had tried to introduce the concept of programming. So they had stored the program in a certain way. But in order to change the program, they had to literally move the gears and try to reprogram it. Okay, so this was the computer of the 40s. And you can see this is how it has grown over several decades. Okay, so this is the board. This is the motherboard we have in our computers today, and the circular part here, the one that I've highlighted, is the processor, like you might know, and you have several other peripherals like the memory, the PCI Express, the SATA, the CMOS, etc. So you can see the drastic change and the evolution of the processor design from the 40s to what it is today, right? So this is how the processors have evolved. So if you start from the 80s to, let's say, the early 2000s, you can see there are lots of features that have got built into. So mainly the idea was to make the system more compact, improve the performance, improve its reliability, so that you can do more work with it, and put in more memory so that you can store a lot of data. So that was the whole idea how it evolved, right? So if you see each of these, right? So here, so they brought in different features into the processor to improve the performance. For example, we'll go through a few of these later on, but just to explain the slide, so they brought in what is called instruction pipelining. That is, you include more and more instructions per cycle so that you can process it at a higher speed. And then you introduce a memory which is on the processor itself, right? So that is what is called a cache, and so on. So improve the execution of the processor as we move on. That is what has been happening over the last few decades. And this graph shows the improvement in the clock speed, and you can see the drastic improvement. It started off with 16 or 8 megahertz, and now we are at 3 gigahertz, and it has been kind of stagnant at 3 gigahertz. Okay, so that is how the processor has evolved and the speeds have evolved over the last few decades. And if you look at this slide shows, so in a processor we have both logic and memory, right? So the logic, the speed of the logic has mainly increased, and it kind of works at 3 gigahertz. But then if you look at the memory speeds, the memory hasn't really it hasn't really progressed at the same speed as that of the processor, right? So the technologies of both processor and memory are quite different. Therefore, you cannot really get the memory to really work at the same speed as that of the processor. Also, the memory is off chip, that is, it's outside of the processor. So it takes time for you to send the data to the memory, and so this is what is typically called as the performance memory latency gap, or the memory and processor performance gap. So even though you have tried to improve the processor and tried to put in more and more features in the processor and try to execute instructions faster, you've not been able to get the memory to work at that speed. Okay, so the memory that I am referring to is the memory that is outside of the processor. So for example, I'm talking of, so this is the processor and these are the memory slots. So I'm talking of the memory access to this, the access to this memory. Okay, so that has been not as fast as the speed of the processor. So what they came up with was the idea of a cache. So the cache is actually it's a small memory which is sitting inside the processor die, right? So for example, so this is the processor, and there is a small memory which is sitting on that same die as that of the processor. So you really don't have to go outside of the processor to fetch in data. So that kind of makes it really fast. On the other hand, you can't really have a lot of memory on the processor die, because the processor die, as you can see, is pretty small. So you can have a very limited amount of memory on the processor die, and that is the trade-off you make for performance versus area, right? So that is a cache which sits on the processor die. So now there are different levels of hierarchy in the cache itself. Okay, so the first one, which is closest to the processor, is called the level 1 cache, or the L1 cache, and the one which is, and that L1 cache is really small in area. Okay, so for example, maybe a 16 KB or a 32 kilobyte L1 cache, and the processor first tries to look for data in the L1 cache, and if it cannot find the data in the L1 cache, it tries to go to the next level, which is called the level 2 cache, which is also on the processor die. So all caches are on the processor die. Okay, the level 2 cache is slightly bigger than level 1, and there is higher chance of we finding data in the level 2 cache than the level 1 cache. So you can look at the hierarchy, right? So these days we have up to 4 levels of caches. So level 1, 2, 3 and 4. And if we cannot find the data in any of those levels of caches, we go to the memory, right? So now you can see the performance is expected to improve because of the caches. Okay, so that is the distance from this triangle just shows the distance of the cache from the processor, and also it indicates the sizes of the memory relative to the first level of the cache. The bus width would be based on the data size. So if we are using a 32-bit data bus, so it will be a 32-bit data bus all the time. So the access time will be with respect to that data bus. So you can't. So the data bus is really an interconnection on the processor or on the board. So that can't be dynamically changed. So that will be fixed for a particular processor. So all we can change is the levels of caches and the sizes of these caches. So another interesting thing to note is, so if you look at this picture, so this is the picture of an i7 Haswell core, and these days, you know, processors have multiple cores, and each of these cores will have a die of its, it will have a cache of its own. So we saw there was a level 1, 2 and 3 and 4 levels of caches. So each of these cores will have 1, 2 and 3 levels of caches. And the fourth level is usually shared. So here it's an L3 shared, but you can have an L4 shared cache between all of these cores. So the idea of having a cache on every core is that each of these cores can work independent of the other core. So that's the whole idea. So in this picture, you have an L3 cache which is shared amongst all of these cores, and you can see the size of the cache is quite big. Okay, I'll show you another picture where you'll see an even bigger cache. So what this semiconductor industry has been doing is, every generation, the transistor sizes keep reducing, and therefore you have more amount of space on the die. So what do you do with that more space is they've been trying to put in more cache. So that's the only way they've been trying to improve the performance so far. And put in more cores and put in more caches. So that's how they've been trying to improve the performance. So all of these there are other methods of improving performance, but these are the main methods of how they've been trying to improve the performance. Yeah, so all of these accesses will have to be protected so that the processors don't really get into each other when they access the data. So if you look at this picture, this is an old Pentium M processor. So this one that I've highlighted, the red box here, is the amount of cache that they had. So that's a significant space on the processor die. Almost up to 50% of the processor is occupied with the cache. So the other blocks that they have are dedicated to, for example, memory management or instructions for pipelining, micro operations, predictions, and stack management, and so on. So, but the whole point is that they have a huge dedicated space for the cache itself. Okay, so cache is an important topic of research because of this sole reason. Okay, so coming to the topics of my interest, specifically in the architecture area. So these are the three things that I'm planning to look at or have started to look at. So in caches, so we saw that we have different levels of caches. We have done everything that we could to improve the performance. So what people have been trying to look at lately is, can we put in more data into the cache by compressing the data itself? So compress the data even further. So if there are similar blocks of data, store one data and keep a pointer to the multiple data. So that is compressing the data. And after you compress the data, how do you place it in the cache is called compaction. So that is one area. How do you compress data and put it in the cache? The second topic is, so we want to keep improving the performance of the processor. So now what does a processor do? It just keeps executing instructions, right? So for example, if we want to do an A is equal to B plus C kind of an instruction, so that is a very high level program definition as per our understanding. Now that gets translated to some kind of an assembly instruction. Let's say we are doing using an Intel processor, an Intel x86 processor. So that will get translated to some kind of an add instruction inside the processor, right? So now the processor is busy executing a lot of instructions. So you'll have a sequence of instructions, and we want to keep executing these instructions really fast. Fast in the sense, one per clock cycle, right? So now in order to keep this happening, we have a set of instructions which we call a pipeline. Okay, pipeline is, you can just imagine it as a sequence of instructions, and we want to always keep doing one per clock cycle. So in order to do that, sometimes the data may not be available all the time. So we want to see if we can predict that data beforehand. So I'll come to each of these later. So that is prediction mechanism. So when we do prediction, there can be a security loophole that again I'll come to, which is the third aspect, which is the security aspect of the prediction schemes. So these are the three areas that I am trying to pursue right now. Okay, so I'll come to each of these. Instructions per clock cycle. So if the clock cycle can be very small, but typically it has to be at least one per clock cycle, but it is difficult to get one per clock cycle. Yeah. It's difficult to keep executing one per clock cycle because the data may not be always ready every clock cycle. I'll show you an example of why we can't do one per clock cycle. One, at least we try to hit as close to one per clock cycle. Correct. So usually the trade-off is based on the application that you're targeting. So for example, if you're trying to target a server kind of a system, a high-end system, then you want more cores, you want to process more, and you also want higher cache. And if you're trying to look at, say, a mobile application or a gaming application, again the target is different. So usually they try to play around with all of these numbers and come to a conclusion as to how many cores can fit into that die and how much of cache. So they do a lot of benchmarking to see if you run this particular benchmark, so how much can you yield with this configuration. So arriving at, so that is called a design space exploration. So that is a whole research topic in itself, and they will arrive at what is the best configuration for that application. Yes. Yeah, it's a complete process of the any. So if you want to interact with the cache in that particular core, it is again independent. If you want to interact between the cores, there will be a shared bus to interact. Again, there is a shared bus to interact. Yeah, usually there will be some kind of a protocol based on which, so that there will be a control unit which controls that. It will be based on which is the higher priority, who wants based on a priority mechanism. Any questions? So I'll try to get into each of these now. Okay, so the first one that I'm showing, the set of data that I'm showing is just the data. So data is all, it's just zeros and ones. Okay, so now we have a set of, each of these is containing 8 bits of data, and we have 16 such blocks. So this is just an example of how we can do compression. Okay, so the first topic is cache compression. So we want to compress that first set of data. Now how do we compress it? So what we try to do is we see if there is, so we can compress data only if there are similar patterns. Okay, so for example, here you have 0, 0, 0, 1, 0. So 1, 0 is the first data, and we want to see if 1, 0 is occurring again. So 1, 0 is occurring in block 0, and 1, 0 is again occurring in block number 6 and in block number 10 and so on. So instead of saving that 1, 0 so many number of times, we want to just save it once. Okay, so that is in the second. Unfortunately, I can't move because of this, otherwise I would have shown what I'm referring to. So this one, so we have 1, 0 here, okay, and 1, 0 here, right? So we want to compress it and put it here. But after you compress, you should be able to decompress it. That means you want to be able to recover it, right? So how we do it is, we have a set of pointers for each of those 16 blocks. Okay, so this is block 0, and we want to say that this has been put into block 0, right? So that is what we are showing here. That first data has been put in block 0 here. Okay, and again, this is going to be put in block 0, right? So therefore, this block 6 is again indicating 0. That means we have put that content in block 0, right? So that is a pointer which is telling us where we have put that data. So essentially we have compressed, so similarly with others, so we have compressed that 16 blocks, 64 bytes of data into a smaller version. Okay, so this is just one way of doing it. There might be multiple other ways of doing it. So now all we have to store is this particular compressed data with those pointers. Okay, so now what happens with this is that we are storing less data, so that means there is more space in the cache to store probably more other data, right? And therefore, we are saving the processor from going off chip to capture data from the main memory. So we are reducing the number of off-chip accesses. And therefore, also we are trying to reduce the memory footprint by compressing this data, and therefore we are trying to improve the performance. Okay, so after we compress this data, there is also another thing called compaction. So what is compaction is, so let's say we have a structure of a cache. Okay, so this is a structure of a cache, one such cache where there are 8 columns and there are 8 rows. Okay, so we can place this data wherever we want. Now where do we place this data? So that is what is called compaction. So now we have compressed this data. Now how do we place it? So if there is 64 bytes, let's say we have this data A, which cannot be compressed at all. And there is this data E, F, G and H, which has been compressed. Okay, 64 bytes has been compressed to divided by 4. Okay, so now there are 4 of these blocks, each 16 bytes. Now I can place this anywhere I want. Now how do I place it? How do I place this data? And if I place it, I have to place it in such a way that if I now remove this data and then put in some other data, there should be less problems for that replacement scheme. And I should place it in such a way that I don't have to put in more effort to access it. Okay, so that is how I need to place it. So now let's say we have this data called L, and there is another, there is an empty space next to L. So now if I get in another data, I can potentially put it there, right? So I want to figure out how to put in the compressed data, and that is what we call compaction. Okay, so this is one area of research. So we will try, there are several ways of compressing data, and there are several ways of putting it in the cache. Okay, so that we reduce the number of off-chip accesses. So that is one area I'm trying to look at. So the next, I'm not sure of graph. Okay, that I'm not aware of. So here basically the idea is you try and place it such that the number of misses, the cache misses are minimum. So that if you want to replace it, you don't want to be keeping too many empty blocks. So for example, if I don't put in, if I put in EF here and CH here, I'm wasting 2 spaces here and 2 spaces here. So I don't want to be wasting space, and at the same time I want to be reducing the number of misses. So there are different ways of placing it. They perform well against certain benchmarks. Correct. 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 So are you aware of any foundational study or theoretical study on bounds on the number of cache misses, or has anyone looked into more formal study of this cache? So you're referring to more theoretical. Yeah, theoretical, I'm not sure. So usually they run the spec benchmarks and then use. Yes, so there is this what is called as a CPAC compression algorithm. So it tries to recognize the number of zeros and tries to, if there is a repeated zeros, then it will try to compress it and then put it. There are others which are based on log 2, log 10 kind of compression. So there are a lot of compression algorithms available. So data 2 is comprising of G and H, you're saying. E and F. Data. Yeah, it depends. Yeah, if space is there and if its compression is the same, then it will go into G and H, into that area. It will go to somewhere. Yes. Static RAM. Static RAM, yes. Yes. Uh, yes. Yes. Correct. Yeah, so that is actually a big challenge as to which so when you're doing fetching instructions, for example, let's say there is a branch instruction, so it is really difficult at that point of time to predict whether that branch will be taken or not. So it is a challenge actually to predict which memory will be fetched, and if it is fetched, it might have to be removed because it may not be actually accessed. So that is actually a big challenge. Yes, yes, yes. It does, yes. Right. Right. Yeah, I think so, yeah. So because if you have contiguous blocks, it's easy to fetch that data and then access it. Spatial locality. Yeah. Correct. So though so much, yeah, because you need more algorithm to in order to keep track of. Say for example, you have I didn't go into details. There is a tag which keeps track of which data has been put in where, and the tag has to be really big in order to manage the address, etc. Yeah. Yes. Yes, so the memory management unit will do all of this. So there's a huge chunk of memory management. Yes, yes, yes. So the algorithm will be the same, but it'll have to keep running. Yeah. So I'll get into what is the need for prediction quickly. So this is a famous example which everyone keeps giving. This is an example of a laundry. Okay, so we have, let's say, a washer, a spinner, a dryer, and then a cupboard. Okay, so now each of these can be done separately. Like you can have one person do all of these, finish all four, and then get into the second person now can get into again the washer, spinner, dryer, and cupboard. Okay, so now if this happens, then this is a sequential thing, right? So instead what we can do, there is a separate washer, separate spinner, separate dryer, and a separate cupboard. So after the washer has been used, the second person obviously can come in and use the washer. So that is the whole idea of what we do in pipelining. So here, so that is what I show here. So after the washer is done, person B can come and use the washer. So that really speeds up the whole process. So that is actually the basis of how an instruction pipelining is done. Okay, so this is a typical classic 5-stage pipeline. So what happens when we execute instructions is first we have to fetch the instruction, that is called instruction fetch, IF. Then we have to decode that instruction, that is what is that instruction going to do, that is instruction decode, which is ID. Then we have to actually execute that instruction. For example, if it's an add, you have to add 2 numbers, let's say. So that is the EX, the execute stage. And then if we have to write the data to memory or access memory for some reason, that is a memory access stage, which is a mem stage. And then if you have to write the data back, the executed or the calculated data back, you have to do the write back stage, which is called the WB. So now you can see if there was no pipeline, you would finish all the 5 and then start executing the second instruction. So now with the pipeline, you can actually, once you do fetch of the first one, you can actually go and fetch the second one. and so on. So this is ideally 1 per clock cycle. So you start fetching 1 instruction per clock cycle. So that is, let's say, a set of instructions, and you start fetching 1 per clock cycle. So that is the ideal scenario if we are able to do it. So now consider this example. Okay, so without getting into too much details, let's say we consider the first 2 instructions. So the first instruction is doing an add of T1 and T2, and it is storing the result in T0, let's say. Now that instruction has been fetched, okay, in the first cycle, and the computation has finished in the third cycle. So it has computed T1 plus T2 in the third cycle. Now the second instruction, which is subtract, is doing a subtract of T0 and T3 and putting it in T4. Okay, so now you can see there is a dependence of T0 on the first instruction. So unless T0 has been written back, so T0 is written back only in step 5, which is the write back stage. So till then my exact correct value of T0 is not available. So if I now start executing subtract with T0, I will be executing it on the wrong T0, right? So in order to get the correct T0, I'll have to wait till this cycle number 6 or at least 5 till it writes back. Okay, so how do we solve this problem? So that is called as a data dependency. So how do we, because there are always going to be data dependencies, because there are limited number of, so what are these T0, T1s? They are registers. So we have limited number of registers, and we don't have like infinite resources, and therefore there are always going to be data dependencies, and therefore we cannot really do instruction fetching and executing every clock cycle. So that is one of the reasons why we can't do one instruction per clock cycle. Now how do we, sorry? Yeah, we can, there are lots of methods of doing it. You can steal it from the pipeline. So for example, after the execute stage, you can steal it from there, but you still have to wait till that execute phase finishes, and then you can do that. So what people were doing initially was just wait. Okay, so just wait till that write back happens, and that wait is typically called as a stall. So you stall the pipeline till you get the data ready. So that is one way. The other way is, if there is any other instruction which is not dependent on T0, fetch that. Okay, so for example, the same example, now you have a third instruction, let's say an add, which is doing add T5, T6. It is not really dependent on any previous instruction. So you fetch that instruction first. So you move the instruction ahead. Okay, so like I show here, you can move the instruction ahead, up, so which is called out of order execution. So you actually executed out of order, but overall the program's intent has to be maintained. You don't change the intent of the program, but you just move the instruction one step ahead because there are no dependencies. So that is one another method of doing it. Another way is, now let's say we predict that data. So we wanted T0. Now can we predict what T0 can be using some kind of a prediction mechanism? Okay. So that is one of the research topics, which is called data value prediction. So for example, if you look at this piece of code, okay, so there are two things that you can predict, or which you need to predict. One is, let's say you have the first for loop. Now am I going to enter into that second for loop or not? Can we predict that? So that is called, so that for loop is going to be translated into what is called a branch. So can I predict that branch, whether I am going to enter the branch or not enter the branch, right? So what is that going to depend on? It's going to depend on the value of val here in the first for loop. If that value is 0 till max, I am going to enter that for loop. So can I predict that well in advance? So that is called branch prediction. So the second thing that we can predict, or we want to predict, is the value itself, right? So like in the previous example, can we predict the value of T0 itself? So for example, in this second one that I have highlighted, if val is 0, R1 is always going to be 4. So if I keep seeing this pattern multiple times, I can probably predict that R1 is going to be 4 and assume and do my calculations. If I'm going to be wrong, we will remove it later on. But at least for a first predict, can I predict that value? So that way, what we can do is we can prevent these stalls. So I can assume the value of T0 and move ahead with my calculations. Okay, so of course there will be a penalty if you mispredict it. So that is later on, but can I predict is the first question. And with what accuracy can I predict? Okay, so that is a second topic of research which is widely looked at, data value prediction. So mostly for server platforms they want to look at, Qualcomm is interested in looking at this mainly because they haven't, there's a lot of literature but then it hasn't been really applied to server platforms especially. So this is another topic that Professor Subir and I are trying to look at. So that's called data value prediction. Okay, so here we can potentially prevent the stalls, and if you prevent the stalls, you can try to get your instructions per cycle close to 1 as possible. So that means you're improving your performance. So it can be a completely hardware which is controlling it, or it can be just a software which is trying to run and predict the data. So it can be both. The first thing that during any prediction what we do is, what is the prediction accuracy? So we can probably predict R1 equals 4, but then how many times is it true that R1 is 4 for a program? For example, if you run a matrix multiplication program, that might be true maybe 80% of times. For another program, it may not be true at all. So we run a set of benchmarks and see what is the prediction accuracy. So if this particular prediction, again there are different ways in which you can predict. So there are different algorithms. You can maintain a FSM, you can maintain a finite state machine or a counter to keep track of it. So which particular mechanism is going to work will depend on the prediction accuracy. So you run a set of programs and you come up with that particular algorithm has, let's say, 80% accuracy. Then we go ahead and implement it. It has 20% accuracy, we don't. So it can be done at the compiler level most of the time. So most of these dynamic branch, there are two ways. You can either do statically, that means there is a hardware which always says, for example, there is a branch which is always taken. We can say that branch is always taken, and that is a static kind of prediction. So even if the accuracy is not good for a particular thing, it will always implement a branch taken kind of approach. So we can do a dynamic prediction, so which is more dependent on the runtime execution. So where there are going to be let's say 2 different prediction schemes, and I am going to pick one or the other depending on which one is more accurate at runtime. So there are dynamic prediction schemes as well. Correct. So for example, if there is a 0 flag, let's say, so when it is 0, it has to execute a particular thing. So it has to keep track of that status flag in order to check if that prediction can be applied. So there will be a control unit in the processor which will schedule it. So you can I mean, I don't know the name, it keeps changing every processor. So there is a control unit which keeps track of what are the instructions at that particular time and which one to schedule. So it again depends on the data dependencies, like I said. So it depends on, for example, I have let's say this set of instructions. Now which instruction has to come depends on the dependency. So unless unless the processor has to look at these instructions, it does not know which one to first schedule. So the control unit will actually look at these, and if there is anything which is not having dependencies, it will move it ahead. So that is the out of order execution engine, which will actually look at the instructions and schedule it ahead of the other ones. Okay, so getting into the last topic of today's talk. So with these predictions, can there be a security loophole? So that is the question. Okay, so now let us assume that this piece of this piece of program is getting executed. Okay, so and there is an exception. So we all know what's an exception or an interrupt. So it has to go out of this sequence to execute that particular interrupt. So for example, if I get to that interrupt, I am going to go to another set of instructions which is called the exception handling or interrupt service routine, and I am going to execute those instructions and then come back and then execute the rest of the instructions. So this is the typical execution flow. So that means when I am currently at that exception or interrupt, I have not really seen the other instructions, which are the ones that I have highlighted in gray color. Okay, so this is what is typically expected out of an exception handling method. Okay, so now what can happen is, so now I'm working on an out of order processor which has an out of order execution engine, and what it has done is it has gone to this particular, it has tried to access this, it has come to this instruction even before it has gone to this instruction, possibly because of those dependencies. Okay, so it has gone and tried to fetch these instructions before it actually gets here. Okay, so it does not know that an interrupt is coming. Okay, so it does not know that an interrupt is coming, so it has gone and fetched some instructions from that green area and tried to fetch that data, at least fetch, if not execute, at least try to fetch the data into the register or into the cache. So what this set of green instructions highlighted in green mean is instructions which should not have been ideally executed at that point of time have been fetched in. The data which is required to execute those instructions has also been fetched in to the cache or the register. And it may not really, so finally what it knows is that finally it comes to the exception and figures out there's an exception. And it figures out that it should not have fetched the rest of it. But by then, it has actually caused some kind of a micro-architectural change. So what we call is a micro-architectural change. It is not a change visible to the program or to the user. It is not really an architectural change, but a micro-architectural change in the sense that the contents of the cache and register have been modified, okay, which should not have happened. And then it figures out, it goes to the exception, it executes it, comes back and so on. But then what can potentially happen and has happened over the last few years is that this particular area that I have highlighted in green, if that involves access to some particular area in memory, okay, so let's say it is some kind of a privileged mode of access, it can potentially result in leak of such kind of data. Okay, so potentially hackers can actually get into the privileged mode of access and access memory which should not have been accessed. Okay, so this is usually called as a cache side channel attack. So people can actually get into the cache area and then access that particular data which should not have been accessed. And people figure that this is an inherent problem with the out of order execution mechanism. Okay, so we have done processes and instructions out of order so that it improves performance, but there is an inherent flaw in it which can result in such kind of a memory leak. Okay, so how do we prevent it? So there are two names which have been floating around lately, which is the meltdown kind of attack and another called Spectre kind of attack. So all of the processors, all of the OS operating systems have been vulnerable, and they have issued different ways in which you can protect your data and so on. But then people are still working on this area to look at how can we protect our data and prevent such kind of attacks which are inherently there in the processor system. So that is another thing that I'm interested in working. 4 different types of attacks. So one of the famous ones is, it's called a flush plus reload attack. So that is very similar to what I have shown here. So what happens is you have accessed some data which due to your out of order execution, and then later on you're figuring out that it should not have been accessed. So you're basically flushing that, meaning removing that instruction, and then again trying to reload it. So basically that is a flush plus reload. That is the most famous kind of attack. So when you are which is very similar to this. So for example, you can access an array, and let's say that array is like a multiplied by 10, for example. So you can, a can be anything, and multiplied by 10 can actually get into some area in the memory which you should not have accessed. Let's say a privileged mode access. So then you can actually get into that loop and then keep accessing that data again and again. So that is one. There are other, the 3 more kind of attacks which I'm not really very sure about. Correct, correct. So that is another way in which people are trying to look at. But then, um, again, it's a trade-off between how many times out of order is going to help us, and how many times is this attack really going to happen. Unless a hacker is actually sitting there and trying to access that particular cache, it is not really a danger, because that content is anyway going to be removed. It is never going to be used unless, so during that time when that cache is having that content, somebody can actually tap that content. So, but unless a hacker is really sitting there and doing it, out of order is most of the time useful, which is why most of our processors are working at that rate. Yeah, again, there are two things. One is, that is true, but then unless, I mean, it's a potential side channel leak. I mean, potentially, if that data is brought into the cache, somebody can actually go and tap the data. So unless, no, I think maybe Vivek can probably pitch in, because I think people are quite smart enough to go and fetch the data at that rate. Yeah, so this, correct. Side channel attack. Correct. No, this is, so I'm saying this is, you're right. So there is a cache and it's a potential side channel to leak the data. So now if there is somebody sitting there to access that, let's say an OS, I want to access that system privileged mode and what the data from that kind of a mode, some hacker can actually go and fetch that data from the cache, which is sitting there without being used. Right? It can be a potential side channel leak for somebody. Otherwise, there is no need to leak data at all. Yeah, so typically there are these processor simulators typically. So there is an open instruction set architecture called RISC-V, which is picked up lately. So you can actually implement it on this RISC-V architecture, and that is acceptable. If you, and again, set of benchmarks like spec or parsec or other types of benchmarks. So, so it will be difficult to implement. So there is another simulator. Recently they have come up with different types of simulators, so which already implement a set of instruction set architectures or ISAs. So they have this x86, ARM, Spark, MIPS, and all of those implemented in that simulator. So all you have to do is that it's like a black box. You don't really have to know the architecture, but you can just apply your piece of code on that particular architecture and then run these programs and run these benchmarks in order to prove your algorithm. So typically it's done that way. Runs in that particular simulator. I can apply it on any of these ISAs, x86, Spark, ARM, whatever, TI. Correct. You have a set of benchmarks. Yes, 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 yes. I can also implement it in that simulator itself. That simulator is again open source, so I can implement this particular algorithm in that simulator and demo it. So that can go as part of the simulator for the next set of examples. No, that processor itself, that black box itself is variable. So for a particular instant of time, I can fix it as, let's say, 3 cores and then 3 levels of cache and so on. But I may want to play with the cache sizes and so on. So that again becomes a variable. So at a given instant of time, everything is fixed. But then to come up with the processor design space itself is a complicated thing. There are different simulators. There are one of them is called, one of them used to be called Simple Scalar. Another one is called Cacti. Another one is called Gem5. Another one M5. There are multiple of them. Most recent one is Gem5. It's been widely accepted. It comes from I think Berkeley or Stanford. No, this is usually done by groups of a group which consists of both academicians and industry people. So recently there has been this group called Risk 5, which is mainly by this group from Berkeley and Stanford, Hennessy and Patterson, who were the recent Turing Award winners, and a set of people from the industry. So Intel, AMD, others. Huge advantage. They have a huge advantage because they at least can have a reliable thing to test it on before they actually put it on the chip. So it's widely accepted that they use these simulators.